Welcome to chapters 3.3 and 3.4. We're going to compare the different heat transfer geometries that we've developed and introduce the general laws underpinning the laws and equations that we've been using. So I've summarized the different heat transfer geometries that we've looked at, slab, cylinder, and sphere, in terms of the Fourier law, the thermal resistance, and the steady-state heat equation. And just as a brief reminder, to get the integrated Fourier's law, all we did was take the generic Fourier law and plug in the heat transfer area and integrate. And then when it came to finding the thermal resistances, we would take that integrated Fourier's law and compare it to this generic expression, Q equals delta T over sum of resistances, and by inspection determine what our thermal resistance was. In these cases, we didn't worry too much about the sign. We just always defined delta T to be positive. And if you look for the cylinder and sphere thermal resistances, because I've defined the logarithmic term as R naught over Ri, that's always going to be positive. And likewise for the sphere, 1 over Ri minus 1 over R outer is always going to be positive. So don't worry too much about the signs. And finally, for the steady-state heat equations, we just did a shell balance on the geometries. So this is a comparison of everything we've done in the past 2 weeks. Now, the truth is, all of this came from a very generalized form of Fourier's law, and heat is actually a vector because it depends on the direction in which you're considering, and the thermal conductivity is actually a tensor because it can have different values for different directions of heat transfer in the same material. And an example of that would be a crystal where heat might flow more easily in one lattice plane than in another lattice plane. So just kind of a reminder on the vector notation. In Cartesian coordinates, what we have is a line vector for heat flux, and our thermal conductivity tensor has 9 different components, but in reality we would expect most of those cross terms to be 0 even for an exotic material. Probably we're only going to be looking at the diagonal terms. And then our gradient, of course, is just the derivative of temperature with respect to each coordinate direction. And that is the full form of Fourier's law. So if you have heat transfer in multiple directions, you can use this to calculate. Coming to that gradient, it's something that we made an assumption with when we were writing out the Fourier's law for cylindrical and spherical geometries. We just substituted dt dr for dt dx. And this is the justification, is that rigorously the gradient of temperature, or the gradient of a function with respect to r, is just dt dr. If, however, we'd been considering the theta direction, it would have been incorrect to just substitute dt dr. We would have had to substitute 1 over r dt d theta. So this is, that's our justification for why we were able to write down Fourier's law by inspection. Example 8 demonstrates Fourier's law for azimuthal heat transfer in one direction. And so what we mean by this is that we'll assume K is constant and that the flux in the R direction and in the Z direction are both 0. So the only direction heat is transferring in is around the curve of an arc. And so that differential shell we're seeing there represents the direction of heat transfer. So for this geometry, we'll start with the generic form of Fourier's law. We know that K is constant and the two R and Z terms are 0. So basically, we just write down the gradient of temperature and plug it into the expression for Fourier's law. It's slightly more complicated if we consider the heat flow, because then we need to multiply by the area. And so that area for heat transfer is delta R, delta Z. And that might not be intuitively apparent because it is a slightly strange way of viewing the problem, but you know that coordinate axes are always orthogonal. So if you want the direction orthogonal to theta, it's going to be r and z in that plane. And the shell I've depicted here has a delta r, which is sort of like the width of that rainbow, and a length, delta z. So think about it. You just plug that area into the expression for area in Fourier's law. Finally, we arrive at the generalized heat equation, which is the Laplacian of temperature plus the constant generation over thermal conductivity at steady state. What's notable about the Laplacian is that it has the effect of taking the second derivative of the function, and its output is a scalar. It adds each of those differential terms together. This is in contrast to the gradient operator that we just saw for Fourier's law, which yields a vector. So from the generalized heat equation, we're always going to get out a scalar, and that's a general rule with energy. Energy is a scalar, whereas momentum is a vector. So energy is actually a little bit easier to deal with. For Cartesian coordinates, our Laplacian just looks like d squared t dx squared plus so on and so forth for each of the coordinates plus the generation term. So that's quite straightforward. It gets way messier in spherical coordinates if you've got heat transfer in all directions. It's rare that in a general unit operation you would have this complicated an expression for heat transfer, but if you did, you'd know how to deal with it. So what you can do with a generalized heat equation is apply it to whatever geometry you're working with, and you can derive the same result using a shell balance on the geometry, or you can go about it just writing down the generalized heat equation and then applying it to the coordinates in question. I would say if you have any uncertainty, do it both ways and you should get the same answer. But thank you. That's all for Chapter 3, and I will see you next week.